Great. Chris, thank you very much. So I've been asked to give a talk on integrating climate impacts models. And I have to say that we just spent actually the better part of 3 days last week with DOE sponsorship talking about integrating climate impact models with a whole variety of other modeling communities. So I was very tempted to just read you the breakout reports, but I won't do that. I've been tracking down, so John showed this yesterday. He attributed it to Yogi Berra. I've been tracking down this quotation for a long time. I finally tracked it, I think, to Niels Bohr, who is no less an authority on the future than Yogi Berra, and one of Yogi's mentors. He had trouble with the slider, and that kept him out of the big leagues for a long time. But I show this, in fact, because there are at least 2 things that we want to try to do when we think about integrating climate impacts information of whatever sort, but I think perhaps especially about health outcomes with a variety of other modeling communities and type of information. Number one, we want to know something about how the future might unfold. But secondly, we want to know about what the actual sensitivities and vulnerabilities are right now. And those are not the same thing. And it's important to recognize that they're not the same thing. So what I'm going to talk about in my time are several things. First, what do we actually mean by integrating climate impacts? Thinking about health outcomes in a systems perspective, about whether we're just interested in disease or other health burdens as well. The answer to this one is actually quite obvious. I'm going to talk about different levels of integration and the implications that might have for a research and modeling agenda, and then what might the future hold in terms of, not so much in terms of health outcomes, because you all talked yesterday about that, and we'll talk more about that this morning, but what might the future hold in terms of research emphasis that would assist us all in understanding these consequences better. So let me start by this question of what do we actually mean by integrating climate impacts. There are a growing number of integrated reports of climate impacts, most of which include some discussion of health outcomes. These are all from a climate change perspective. In the U.S., we've now had 3 U.S. national climate assessments. The one on the right, on the left-hand side of this slide, as you face it, was the first U.S. climate impacts assessment, the first national assessment, about 15 years ago, which included actually a very nice chapter on health risks, the conclusions of which would still seem very familiar to everybody in this room today. There's been, sadly, less progress than one would have liked in the underlying quantitative science. The second U.S. national assessment had by and large similar conclusions. That was about 5, 6 years ago. By and large similar conclusions, a little more confidence perhaps in some of the statements. And then the third U.S. National Climate Assessment was published just this past spring. And this, again, as many of you know, because several of you participated in this, again, had really a very nice chapter on what we know about health outcomes with respect to climate change in the U.S. In this last assessment, we have moved, actually, and interestingly, from a discussion of climate change as an issue that will affect us in coming decades to a cogent discussion that things are happening right now. Right? That this is not just an issue of what will happen in the 2030s and 2050s and, you know, heaven forbid, 2100, but what is happening right now that is the result of change and variability in the climate system, some of which can be attributed to our actions, some of which cannot. But we make the case strongly in this assessment that in a sense, the parameters of the discussion have changed. That this is not an issue strictly for our children or our grandchildren, but it's an issue for us to think about, to understand, and to deal with now. that we're already feeling many of the effects of increases in some types of extreme weather and sea level rise. And by the way, it is not true that for particularly large events we can say nothing about whether or not they're related to climate change. I can guarantee you that not a major storm, not a heat wave, not a drought occurs anymore anywhere around the world than the climate science community immediately follows that with a raft of papers, most of which calculate the probability that an event that large or larger would have occurred in an unforced climate. And the results from those studies are almost always that climate change attributable to human activity has increased the frequency of these types of extreme events. And we see impacts in every sector and in every region of the country. They're clearly not identical, but in many important sectors in the U.S. economy, we are seeing impacts, and this includes the health sector, but it also includes water, agriculture, the energy sector, and many more. At the same time, there are many actions that we can take, both in terms of mitigation, to try to reduce the atmospheric forcing of changes in the climate system, and to adapt, to prepare for change, either to adapt to changes that are happening now or to prepare for impacts that we can't avoid. The second set of assessments that we've seen to try to integrate in a qualitative sense climate impacts information, of course, is IPCC, and in particular Working Group 2 on impacts, adaptation, and vulnerability, where for the first time the assessment was formulated explicitly for the most part, in a risk-based format. And with a thorough, really an exhaustive documentation of the kinds of impacts that we're seeing around the world in different sectors. This is an extremely busy slide, but what it tries to depict with all these different icons for physical systems, for biological systems, for human systems and managed systems, is where we have documented evidence in the literature that effects exist, and whether those effects have climate as a major driver, in which case these icons are filled in, or whether it's it's one among many drivers, in which case the icons are open. And so you can look literally on every continent, and in many places the literature will already reflect that there are health and economic impacts, and moreover that adaptation makes a difference. And so this is also a very busy slide which I won't go through in detail, but the difference between the full length of these bars and where the blue is you can think of as the difference between impacts without adaptation and how much adaptation we think can actually lessen that burden of impacts. One of the striking features of this chart actually is that there is far less capacity right now to reduce some of these kinds of impacts in the developing world than in the industrialized North, which should be no great surprise to us. So one question is, why isn't this profusion of assessment literature actually sufficient? They all conclude that risks to health from multiple pathways, disease, heat stress, waterborne illness, recovery from events, malnutrition, that these kinds of risks from multiple pathways will actually increase. There hasn't been an overall assessment related to climate change impacts that I'm aware of that concludes that the risks to human populations of health impacts will actually decrease. They're all extremely cautious about actual health outcomes. Most of them have couched their language in terms of risk, in part because whether or not adaptation is included or not is highly variable in the underlying literature. So I would suggest that one element of integration that we're actually mostly missing is whether or not health impacts are considered in integrated modeling studies. And here I think we need to distinguish three types of studies. One way is sort of one-way modeling studies. It includes climate variables as additional drivers in both disease and non-disease pathways for health outcomes. This is actually a lot of what we heard yesterday. And so there are actually quite a number of modeling studies like this, sort of classic climate impact studies. One-way modeling that actually starts to include adaptation and institutional responses so that we can come closer to health outcomes, actual health outcomes, rather than simply an assessment of risk. Rather than assuming that today's health system and institutions will be the same that we will see in 2030 and 2050, something that we know is not true. But is actually a very common assumption in many climate impact studies, not just in the health sector, but in many sectors. We could go all the way to two-way modeling, which actually starts to include the feedback from health outcomes and adaptation, both on the economy and on subsequent consequences for both mitigation and future demographics. So that would be a complete integration of climate impacts and impacts on health into a study. So again, just if you think about these as different categories, there's lots of research, and perhaps not as much in the health sector as we would like, but certainly in other sectors, there's a lot of research that does this. It starts to look at climate impacts, and by including variables as climate variables as additional drivers. There's some research. I couldn't figure out how to make a check that was dashed. This is my rudimentary PowerPoint skills. There's some research that actually starts to include adaptation responses, but not very much. And there's no research essentially on this type of two-way modeling that actually looks at feedbacks from changes in health outcomes to the economy and feeding back into future economic and demographic change. So one thing I did was I drew the simplest systems diagram that I could think of to try to illustrate this point. And this diagram is so simple that nothing shows up. Oh, okay. So if you want to think about change in the climate system and climate impacts, you can think about a whole set of socioeconomic drivers that drive changes in technology and emissions, that drive greenhouse gas forcings and the like, aerosols, black carbon, brown carbon, and that these drivers of the climate system affect the physical climate system, which then, and I'm only going to think about health here for a minute, has a set of direct impacts, heat waves, and so forth, and indirect impacts, zoonoses, food security, water availability, storm events. But those actually act through a whole set of access to health care, institutional issues, public infrastructure, until we actually get to outcomes. But this is not a complete system because the health outcomes themselves actually, we know, have both economic consequences and in many parts of the world have really important or the potential for really important demographic consequences, which themselves feed back. So this is the simplest systems diagram at a large scale that I could think of. And I can't think of a single study that goes all the way around this circle. Not one. I would love to see it. It would be really fascinating to see. But I can't think of any that does that. And of course, any one of these components could itself be expanded into its own systems diagram. So the complexity of the system is partly a function of what we choose to model. At what level do we want to try to grapple with the system? So one big question which I think we actually have to confront is, to what degree do we want to think about health impacts in a systems context? Do we want to think about them as part of an overall climate demography system as in that previous slide, or do we want to think about them as an impact sector that has its own forcings and responses, behavioral responses and interventions that we could model, in a sense, taking the right-hand part of this diagram and fleshing out the systems aspects of these boxes here on the right. We've heard both perspectives, and we've actually in the last 24 hours we've heard sort of both perspectives and seen some examples, for example with AGMIP, where for the agricultural sector they're much closer to thinking about this in a sort of very integrated climate context, at the same time as they're still interested in understanding the actual agricultural and food security responses. So why would we do this? I mean, yes, these systems are complex. That shouldn't be a deterrent. But we should be clear about why we're actually trying to do this. And of course, one big reason is strictly scientific. We want a better understanding of the impacts themselves, especially when they're the result of multiple factors. I can recall very early in my career when I worked on acid rain issues and air pollutant effects on forests, getting a lecture on Koch's postulates from a very distinguished forest pathologist that was both entirely correct and exactly wrong for the problem at hand, because it had no appreciation for the complexity, in that case, of forest ecosystems as systems that respond to multiple factors, but have very limited, sort of, in a sense, sort of response variables. A second reason that we might want to do this is actually to develop the capacity to generalize from one situation to another, or to recognize when this is difficult to do. If you were to go back in the first U.S. National Climate Assessment, and you were to read the 2 or 3 paragraphs on vector-borne disease, which I can assure you were painfully negotiated, perhaps with some of you in this room, between the lead authors, the community, and then between the lead authors and the overall synthesis team, you would see that in effect those paragraphs from 15 years ago say, well, with respect to what we know about vector-borne disease and climate change, we can say with absolute certainty it depends. And because it does depend. It depends on some very complicated biology and ecology, relatively little of which was actually understood at the time. We heard a couple of really excellent talks yesterday about situations where that kind of systems, what is essentially systems ecology, is much better understood in particular instances now. But a third reason that we might want to integrate impacts information is slightly different, and that's the ability to target interventions to reduce vulnerability or the incidence of harm. These are not the same thing. In particular, designing interventions may or may not depend or demand the same degree of understanding of processes that some of the other scientific goals do. And we can all think of situations where they don't. We can also all think of situations where they do. Where interventions could be, you could design the wrong intervention, you could think that you were affecting something that you really weren't, or you didn't understand the causal pathway well enough to know what intervention to do. But we can think of other situations where not understanding every process level detail of the impact system doesn't actually detract from a particular set of policy interventions. And so we have to, as part of this, we have to think about scaling issues at the same time. Is it always the case that local information is required? For some kinds of understanding, knowing that Aedes will breed in standpipes in Singapore and overwinter in sewers, the answer is actually yes. You really do need that kind of highly resolved local information. But somebody's going to have to convince a very large policy community that level of local information is actually required for regulating primary and secondary air pollutants. It's manifestly clear that it is not required in order to design those kinds of interventions. It may be required to understand in detail all of the consequences of those interventions, but the design of those interventions long predates the ability to generate that kind of local information. And I think none of us would argue that they weren't worth it. In fact, every time somebody has actually tried to do the study, they're more than worth it. Temporal scales. Are we actually interested in dealing with the aftermath of events, spikes in the frequency of disease, or understanding longer-term trends in both forcings and consequences? This is a really well-known challenge in environmental issues, environmental health issues, and a lot of ecological issues, especially when the mechanisms are poorly understood. We have, in a sense, one of the challenges we have in climate change is this long time span of changes in the forcing, where actually in the present day we've seen this already the decades of forcings and changes in the physical environment, and much of which is manifested by changes in events, frequency of events, severity of events. So untangling these can be difficult, but we actually have to be explicit, I think, in constructing systems models and actually using them in a sensible way. And then the third element of scaling is process resolution. How much process level mechanistic information is desired versus how much can actually be parameterized in a systems context. All systems modelers face this question. There is nothing new about this, but what there is, I think, is in each domain, scientists and modelers have to make some choices about what can they parameterize sensibly, what really does have to be modeled explicitly at a mechanistic level, and how do you test and evaluate the consequences of the choices that you've made in sort of how deep your understanding has to be in an overall systems model. So do the models we have actually span this broad perspective? Well, mostly not. The models that come the closest, I think, are actually integrated assessment models. These are models that in principle integrate a whole variety of human systems with descriptions of the physical Earth systems and pass information back and forth about greenhouse gas emissions, about land use and land cover, and then pass information back to human systems. Some integrated assessment models have focused on cost-benefit analysis. These are highly simplified models. They tend to have a handful of equations to describe the entire global economy, but they're built for a particular, and a handful of other equations that describe the carbon cycle and the physical climate system. These are so reduced form. They're designed basically to do one thing, and that's cost-benefit analysis for sort of the optimal choice of policies. Another whole family of such models have focused on cost-effectiveness analysis, so they don't attempt to do a full cost-benefit analysis. What they do is evaluate the cost of any particular mitigation pathway. And they've got much more complex representations of different components of the economy and different components of the physical system. And this community has actually been doing quite a lot of modeling experiments and simulations with one-way modeling of impacts. Explicit introduction of water, an explicit description of agricultural productivity and land use change, mostly focused on physical and biological impacts. They're rarely taken all the way through to human health or economic consequences, although I think the machinery for doing that, for at least some types of health impacts, in particular those related to extreme weather, is probably there. I know there's another one. And right now, no integrated assessment modeling framework has a feedback loop from any of those health-related impacts to demographic change and then back into greenhouse gas emissions. Right, so we know empirically that that's important, But there's no modeling group that has yet taken that step to try to sort of complete the loop. So as a consequence, they all take demographic data and population data as a specified input. Usually from the UN population scenarios. There's a whole group of scientists, both economists, other social scientists, ecologists, who've been working very hard the last several years on designing a new set of both socioeconomic scenarios and ultimately that can be transformed into different kinds of technological and emission scenarios. But this is a real serious research effort, none of which has been, in a sense, coded into these models. It could be developed at a population level, but it will take some thinking and some real work to do in a sensible way. So where could we make progress? So one place we could make progress, and this is both a challenge, I think, and an opportunity, is thinking really hard about where the climate information comes from. You can get, so everybody has to deal with this problem. The health sector is not alone in this. All of the other impact sectors have to think about this problem. You can get very high spatial resolution climate models and climate model output, but you can't get it for long simulations. This is a real, and you can get long simulations, but you can't get it at really high spatial resolution. This is an inevitable trade-off of the just physical limitations of computational time and complexity. You have to be really careful, on the other hand, if you're talking about interdecadal, interannual, seasonal variability, and what you want to do is a simulation that is akin to a prediction. You have to be really careful about what you believe out of the model outputs, or out of the climate models that you're using as inputs, because we have quite a span of either no information about whether those models are useful, uncertain information, meaning that, in a sense, that the climate modeling community will refuse to tell you which climate models are better or worse for a particular purpose, or in some cases, what I've called euphemistically negative information, which means that there are many, many papers in the literature, in particular, looking at interannual variability and phenomena like ENSO, where the climate model being used as input is known not to have any forecast skill. The model is wrong in fundamental ways, but the papers are published because it's an interesting exercise and a useful exercise, essentially in sensitivity analysis. But you'd better be clear about what you're doing, because this will have implications for the uncertainties of results and tracking the uncertainties of results in a quantitative sense downstream. The fact that we can make the computers generate these numbers is not the same as saying that we should therefore believe them. And there are, of course, both statistical and dynamical methods for downscaling climate information. But tracking uncertainty can be extraordinarily difficult. And you will, in fact, in that case, be working in a scenario mode. It's not a criticism. The working in a scenario mode is what most people actually have to do to understand different potential pathways that the world might unfold. So whether we're going to undertake systems modeling at any level is essentially the same as asking whether we understand the systems well enough to make projections, to make predictions, or actually to make forecasts. But you don't actually have to do this forward modeling, right? In the sense where you start with a climate change, you then ripple that climate change through whether it's vectors or direct impacts to get to a health impact and so forth. You don't actually have to address the problem that way. You might do well to turn this problem around and ask instead about the degree to which we understand the parts of the systems that determine vulnerability and sensitivity, and including the underlying vulnerability of the human populations themselves, and then model the degree to which interventions might have an effect, and only then ask the question about whether change in the climate system makes those interventions easier, harder, more effective, less effective. So we could quite easily see a future in which several forms of integrated science and modeling are actually being pursued. Integrated systems modeling at a really high level, akin to that very simple systems diagram that I drew earlier, for understanding long-term trends and evolution of climate health linkages over several decades in the developing world and beyond. Systems modeling at more detailed level to understand particular cases, perhaps to assess the value of particular interventions, or to determine whether or not we understand those particular cases well enough to make a prediction that has some quantitative value, perhaps about Lyme or something like that, where we now really do understand quite a lot about the, everything from the life cycle of the disease organism to the various vectors that control its spread, to whether or not people are inside or outside, and so on and so forth. And a whole range of empirical research and modeling to understand where sensitivities arise and best methods for actually reducing vulnerability. And these could actually be pursued at some level independently of each other with some communication back and forth. But in all cases, we need to understand that this is not just a problem of science. This is also a risk management problem. And so we need to understand, to acknowledge where these uncertainties are, but we nevertheless have a responsibility to manage risks and really to keep our eye on the ball. And I know you can't read this, but what the sign says is, caution, the sign has sharp edges. Do not touch the edges of this sign, and the bridge is out ahead. Thank you. Oh, so that flashing red light means I went 1 minute and 10 seconds too long. Great. So there's no time for questions.
Oh, really?
Sorry.
We'll take a question or two. And as from yesterday, please introduce yourself when you ask the question.
Okay, I'm Gary Girnar from the Department of Energy. Tony, I thought it was a great talk. I do have one question that goes back to your simplistic view of the systems model. And in that, there was an assumption that climate change was a dominant forcing of, let's say, the health impacts. And I'd like to at least remind all of us that it's not just climate change that can affect health, especially when we talked about, let's say, systems failure yesterday. Yeah. There are things like wars, there are blackouts, there are other things where climate change has to be put in context of all the other shocks that can affect society. And I would say in that context, it might be a useful exercise to at least go through some case studies to identify how important has climate change been in some significant health impacts when it's in the context of other forcers that we know are also causes.
Gary, that's an excellent point. And you're right, that's a weakness of that particular way of drawing a systems diagram. It's interesting, you know, one question that none of the climate impact assessments are built to ask, I mean, you'd have to really repurpose them, is whether climate is actually the biggest deal in any of the impact sectors. So some of us are hoarse from raising this issue over and over and over again, because we have impact sectors where we know climate is not the major forcer or the major near-term forcer. But what we actually want to understand is the degree to which it either exacerbates an existing issue or makes it less of an issue. I mean, I think somebody was talking about, I mean, there's a lot of discussion yesterday about heat waves. We already know that some of the really important factors in what happens in cities during heat waves is a function of what the infrastructure is like. It's also a function of whether or not that city has recently experienced a heat wave, right? Because we do, after all, learn, I hear. The infrastructure is not a constant, nor is the behavioral response a constant. So you could have the same meteorological event with two very different outcomes, depending on what has happened previously, and depending on a whole host of issues. And we've seen lots of examples of those kinds of things.
Hi, Ben Zajic, Johns Hopkins. Chris and Tony, those are great talks, really thought-provoking. Building a little on what Gary just said, and really building on the workshop that you and Gary and Bob and others had last week, one thing that was fascinating at that DOE workshop was getting together as a community and talking about experiments. You know, what is the experiment we would use for different kinds of one-way or two-way coupling modeling? And now this
Right.
community, I think, is at some disadvantages in terms of our, you know, diffuse targets as well as, you know, the relative maturity of the tools. But there's also an advantage in that there's a lot of opportunity in that diffuse nature. And so, does it make sense for the community to start doing that, to start planning experiments? And I know that people have done, you know, there's AgMIP, there's the malaria models that were presented last week, but should we just systematically say, okay, here might not be, maybe not even the most important questions, but here are the questions that are tractable in different modeling frameworks and go after those in some experimental sense?
I think it would make an enormous difference, right? I mean, it's how we're going to learn about the degree to which this type of numerical modeling is actually useful and interesting. It's not just whether we could take a, you know, sort of a simple systems diagram and code it up. Our students could do that. Whether or not it's worth doing and whether or not you would learn something new by doing that, I think is the real question. And we're only going to do that by doing a set of experiments.